3.1 Solving Systems Graphically, Part 2. Let's go to work. So we've discussed what can happen here when solving a system by graphing. We could have one solution, no solution, infinitely many solutions. And we talked about getting those equations both in slope-intercept form. So let's start by looking at it. I have one or a system set up here and ready to go. So let me start with the first equation and just go ahead and graph it. I'm going to use red for that one. My y-intercept I can see is 1, and my slope is 2. So go up 2 over 1, up 2 over 1. I'm just doing a rude graph here, which means I'm not really worried about the little things, just making sure we got a good idea of what it looks like. I'll do my second graph here in a light blue, and I can see that my y-intercept is 4. 1, 2, 3, 4. And my slope is a -1. So I'll go down 1 over 1, down 1 over 1. And right away, oops, totally missed that. Sorry about that. Right away, I can see that my points intersect right here. Matter of fact, I can see that that's the point 1, 3. So 1, 3 is the solution to my system. Now, I can check that. I can take this x and this y value, and I can plug it into each of my equations. Let's take the first one. So 3 equals 2 times 1 plus 1. So 3 equals 2 plus 1, and yes, that is correct. Then I can do the same thing with the second equation, to where 3 equals a -1 plus 4. Well, a -1 plus 4 is 3. And I can see right away that 1, 3 is a solution to my system of equations. And that's how we solve systems by graphing. We simply graph them. Well, solving by graphing is sometimes considered to be the least accurate method. And I want to show you an example of why. I'm just going to make something up here. Let's go, I don't know, x plus y equals 3 and 2x minus or plus y equals 4. The first thing I would have to do for this system is I would need to get them both into slope-intercept form so I could graph them. I mean, I could do a t-chart if I wanted to, but that's a lot more work. So on this first one, I'm just going to subtract x from both sides, and that gets me y equals a -x plus 3. Okay, now that's in slope-intercept form, so I'm good there. The second equation, I'm going to subtract 2x from both sides. So y equals a -2x plus 4. Okay, so I have two equations, both in slope-intercept form. Now let me graph them. Now, try to be somewhat accurate in my graph, but it is still going to be what I consider a rude graph, okay? Rude not because it's going to be mean to you or anything like that, but just rude because it's not, exact on my points and stuff like that. As far as I'm just kind of drawing my values, like say that's 1, 2, 3, 4, 5, 1, 2, 3. Oops, see how I undid that. Just not always the same amount, and that wouldn't be good. That's why I call this a rude graph. And most of the time a rude graph is good enough, but that's also why solving by systems by graphing is considered the least accurate method. So let's go with the first equation. We'll go with that one in green. My y-intercept is 3, so 1, 2, 3, and my slope is a -1. So down 1 over 1, down 1 over 1. So that one's going to look something like that, roughly. Okay. Let's go with, oh, lovely orange there. My y-intercept is 4, and my slope is a -2. So I'm going to go down 2 over 1. Well, that's nice. Down 2 over 1. Let's go a straight line from there. Something like that. Again, just rude. So where do they intersect? In this case, I got another one that's kind of nice. They intersect right here at approximately 2 and 1. So 1, 2. Can I plug those in and see if that works? Sure. Is 2 equal to -1 plus 3? Yes, it is. Is 2 equal to -2? Oops. -2 times 1 plus 4? Yes, it is. So that is, in fact, my solution. And in both of those cases, my solutions were nice, pretty lattice points. But they won't always be lattice points. What if I had these two lines? I'm going to use the same graph there. Hope it's okay. But let's say I had this line and this line. Okay, if we look at their point of intersection, it's kind of in the middle. And I don't have integers or nice even round numbers. Well, without technology, I have to guesstimate, and I would have to say, hey, well, this is like a -1 point something. I'll say a -1.5. And the y is also about a -1.5 or 1.5. I would have to guesstimate. And that's not exactly accurate, but we get the idea, and that's okay with a rude graph. But using technology, and that's what I want to do here, is I want to show you how to use technology. And I'm only going to show you this once, so you might want to really pay close attention. And I'm going to give you some crazy equations. Let's go y equals a -2/3 x plus 4. You would have no problem with that. Okay, but how about this one? 2x plus 5y equals 1. And that one would be hard to graph, I'm just telling you. But watch this. I can use technology. What technology, you ask? Desmos. Desmos is our graphing calculator that we use for Algebra 1. It is the calculator that is used on the final exam or the Ohio Department of Education exam that they give you. So first equation is y equals a -2/3 x plus 4. So y equals a -2/3 x plus 4. All I got to do is type it in, and it graphs it for me. Isn't Desmos amazing? And the second equation was 2x plus 5y equals 1. Sorry about that. 2x plus 5y equals 1. 2x plus 5y equals 1. And it graphs it for me. Now, if I were graphing this equation, you can see where this thing comes and intersects. And look at those values, 14.25 and a -5.5. Using technology, we can find a solution so easy. So can you use Desmos? Yeah, you can. I hope this was helpful in allowing you to learn to solve systems of equations by graphing. Have a great day.